questions about anything before we get the least square stuff finished up and then get into Fourier series today? There you go. Goodness. All right. Well, let's finish up what we were talking about last time. There it is. All right. So this is where we left off. No, I'm not plugged in. That's why it's not projected. Try that. Works much better when it's actually plugged in. Okay, so this is where we left off last time. So remember, our whole goal with this process was to try to get some sort of a measure of how much the deviations of your data points, the y values, vary from the mean, is explained by how far your predicted values vary from the mean. That's the whole idea behind this. We're doing it from this linear algebra type of perspective, this matrix multiplication type of perspective, so that we can go in, pardon me, and use Excel to help us do those computations. And then we'll go back and use R and see that we've got the same values. So make sure we get the right answers here. All right, so remember this expression over here is what's giving us that total sum of squares. Down here, we'll talk a little bit more. We already talked about this one, but this is our residual sum of squares. Again, this is the part that is how far your predicted values differ from your data values that you're given, and the square of those, right? So this part over here, we'll talk in a minute about why this is the explained part. But let's talk about why those pieces in the middle really do vanish. And then we really do have this split up into a sum of the squares of your explained piece plus the sum of the squares of the residual piece, the piece that's not explained, this piece is left over. All right, so let's talk about why those are 0. And it's not too big of a deal why. My goodness. Sorry. All right, so let's go back and remember how your error, again, is defined. It's the difference between those things. Your y is your vector of the data points that you're given. Your b is that least squares solution, those coefficients that we're looking for. The x's are those coefficient pieces, so that's how we get our error, right? But remember how we solve for the least squares solution. We did those normal equations. This is x transpose x inverse times x transpose times the y, right? That was how we got that was how we get the b, right? That's how we get our least squares solution, right? Okay. Notice that if we multiply both sides of that equation, well, let's try this again. If I multiply just this thing right here by x transpose, if I had an x transpose right here, this whole thing would go away, wouldn't it? Because I'd have x transpose x and then times the inverse of that same exact matrix, right? I would just get the identity matrix there. Right? Okay. So let's multiply both sides of that equation by x transpose. Thanks, Justin. Let's multiply both sides of this equation by x transpose. I would have x transpose times the error vector, that residual vector, is going to be x transpose y minus x transpose x times x transpose x inverse x transpose y. I know, lots of letters. But again, this part right here is going to be equal what? Yeah, that'll be the identity matrix, right? When I take the identity matrix times X transpose Y, I just get X transpose Y. So what are we left with? X transpose Y minus X transpose Y. We end up with the zero matrix, or the zero vector, I guess, in this case, since the E is 0. So if I take X transpose times E, I get 0. Look at that second term. What do I have right here? X transpose E. That's going to be 0. So that part's going to go away, right? Look at this part here. I've got E transpose times X, and I just realized I didn't have my little arrow, my vector arrows on the top, whatever. If I do E transpose times X, what am I going to end up with? It's still going to be 0 because E transpose times X is the transpose of what matrix? E transpose X is the transpose of X transpose E, right? Remember when we do this product, the transpose of a product, it's the product of the transposes in the reverse order. So this will just be 0 again, right? So that's why these terms go away. Those terms in the middle go away. We get that property that when I take the transpose of X and multiply it by the error vector, we get 0. So those middle terms really do go away. Okay. I want to make sure that we understood why these go away, right? Because we got this expression right here by multiplying out this product. We have inner middle terms, right? We're claiming that they go away, and we can really split up our total sum of squares as an explained sum of squares and a residual sum of squares, right? Explained and unexplained. Residual is what's left over from the when the predicted just wasn't good enough to predict that particular Y. The residual piece. Of course, we want the residual part to be small, right? All right. So when we do this R squared value, that's why we do this quotient. If this quotient is closer to 1, that means that this residual part is small and it's a better model. Because this is a percentage of the total error, total sum of squared error, that's explained by the model's sum of squared error. The closer it gets to 1, the better the model is. So we usually refer to this as a percentage of the error explained by the model. To have an interpretation of what's going on. All right, so let's talk about why this really is your sum of squared. It really is that piece that I talked about last time. Remember that we said from a summation standpoint, this breaks up into an explained part and an unexplained part. We said we recognized this as your Y transpose in Y. We talked about that last time. This is your E transpose E part, right? We didn't talk about why this middle piece has got a lot of stuff in it, is this piece here. Okay, so let's talk about why this part really is this same exact sum. Okay, so going back up to and using our properties of that N matrix, and then I promise this will be the last that I'm going to talk about the theoretical part. We'll go do some numbers, okay? All right. Remember, one of the properties that we said that the N matrix had was that it's idempotent. Idempotent means that when you square it, you get the same thing. So I can put in N squared for N, and I don't change anything. I'll just rewrite N squared as N times N. Okay. Remember, idempotent means squaring it keeps it the same. So like when you square 1, you get 1, for example, right? For matrices, there's lots of different matrices that you can square and get the same number, get the same matrix back again. This N matrix happens to be one of those. Okay. Also, another property that we said the N matrix had was that it was symmetric, which means it's its own transpose, correct? So on this first one, I can put a transpose, and I don't change anything. Okay, so I haven't changed anything. I've just rewritten it. But notice, look at this. Oops, I'm missing something. Aha, I missed it way back up here. There's a transpose on this B. Notice it's right here, right? When I distributed that, I forgot to write it down at the end of the class last time. There's a transpose on there, so there should be a transpose right here, which means there should be a transpose right here. That matters. Okay, so look at your first three matrices all together and your second three matrices all together. What do you notice? What relationship do these three have to these three? It's the transposes, and it's in the reversed order, correct? Right? So this is the same thing as NXB transpose times NXB. Right? Okay. So notice that this has the exact same form as these other things did, right? So this is giving us a sum of squares of something, right? Okay. So let's talk about what that sum of squares that it was. Let me scroll back up and go back up into your notes here, somewhere in here. Right here, this was our total sum of squares, correct? And remember how we got that? It was because when we took n times the y, I got the deviations in each of those terms, so that when we multiplied it by the transpose in front, it squared each of those terms and added them up, right? That was how we got that, wasn't it? Notice we have the same exact situation here, isn't it? If I think about this as a single vector right here, we have the exact same situation, don't we? But rather than having the y data points, these are the y predicted, right? That's the whole point, right? When I do the x times the b, I get the predicted y's, correct? Right? So now these, when I do this product, the n times the xb, I get each individual entry is not y sub I minus y bar, it's y sub I hat minus y bar. Right? The entries of these things right here, each entry is y sub I hat minus y bar, so that when I do that exact same product, I get the sum of the squares. Okay? So that's what it really does give us, our SSE part. Okay? All right. In any event, I wanted to make sure I mentioned to you why this really is what we say it is. Because when you go into a statistics class and do this kind of analysis, you talk about how they're broken up with these terms. This way, we're just attacking it from the linear algebra perspective so that we can use the technology to help us get these products. And then we'll go and check our work with R. All right, so that's the plan. All right, so let's go into that Excel sheet that I sent so we can talk about how we can do the R squared value. Let's see, do I have one of these actually done? Let's do one with these where we haven't done a quadratic model yet, I don't think. I think I just did the first few, right? Okay. So let's see if we do a quadratic model and see what happens. So again, let's just run through the whole process. Let's figure out what the model is and then figure out what the R squared is from the model. Okay. If I were to graph this, we might see why we would want a quadratic model, but you can kind of tell from the numbers what I did. At least I hope you can tell what I did. If I square -3, I get 9. Square -1, I get 1. Square 0, I get 0. Oh, it's -1, but that's okay. Square 4, I get 16. Square 7, I get 48. I just basically took y equals x squared and just moved it a little bit. Play with numbers. But again, if you want to check what type of model might be a good one to start with, you would do a scatter plot. Here's something that looks like this, right? And we see it's got that bend in it, right? So we see something that might be a quadratic model might be a little bit better. Better than a linear model. Okay. I'm going to delete that back out, but this might be a first step if you're trying to figure out what kind of model to use. All right. So again, remember the first thing we need to do is create that X matrix. We're trying to fit this to y equals a plus bx plus cx squared, right? We're trying to fit it to a quadratic model, right? So your first column of coefficients is going to be what? 1, right? Because the coefficient on the A is always 1 no matter what. Your second column is going to be your x's. The third column will be x's squared. Good. So a lot of times if you just highlight a 1 and pull it down, it makes it want to try to count the things you want to do 1, 2, 3, 4 instead of that. So that's why I did 2 of them and then pulled. Okay. Your x values are over here in A2 and then down, column A and then down. So I'll pull that down. Let me zoom in. I guess I'm a little bit zoomed out. And then here we'll do A2 and square it because I want to make sure I have the square of the x values. So when we did the linear model, we just had those 2 columns, correct? Okay. So for the quadratic model, those 2 are exactly the same as what you'd have in your linear model. This one we just have to square. So square, pull down. Great. So again, this is your X matrix here. What do we want to do with that X matrix? Transpose. So remember, command for that is just transpose. There's the matrix I want to transpose, right? We really do get the transpose. What do we do next? Yeah, I need to take that transpose matrix that we just found, which is this one up here, and multiply it by X matrix. Good, this one here, right? So again, remember, we're doing the X transpose times X, multiplying those 2 things together. What size, before I even hit enter here, what size matrix should I get? 3 by 3, right? Remember the square, this matrix should be square and have the same number of rows and columns as you have coefficients you're trying to find, right? So when you do X transpose times X, you should end up with a 3 by 3 in this case, okay? Which we have. What's next? Inverse. So again, remember the command is minverse, right? Matrix inverse. Do the inverse of that matrix. Get those values. What's next? Good. Multiply the inverse, which is this one, times the transpose, which is way back up here again, right? So inverse times transpose. And then finally, the very end here, what do we do? Yep, good. Multiply that matrix that we just found by the y values, which are over here. Well, how many things should we come up with here? 3. Yes, we do. So here's your constant coefficient. This is your constant. This is your x coefficient. This is your x squared coefficient. That make sense? And again, we can check this in R pretty quickly, but this is why we would do it if we were computing it, again, from a linear algebra standpoint and playing around with Excel. And let's be honest, this is the whole reason why I'm doing this, is so you can play around with these different functions in Excel and understand where the things come from. Because in practice, are you ever going to go do this in Excel, or are you just going to pop it in some place that'll give you the values that you needed to start with? Yeah, probably option 2, right? Okay. All right, so let's talk about how we can get the R squared now. I'm going to have to just scroll around, I guess. All right, so the first thing I need to do is create that N matrix. Remember how N is created? Your N matrix, again, is your identity matrix minus 1 over N times the iota transpose thing, right? That's how we created the N matrix, okay? This part right here created a matrix of all ones, so this is just a matrix of all 1 over N's. This, of course, is your identity matrix. Okay. We need to make sure we understand what size we need for these different things. I need to take this N matrix and multiply it by your Y. There are 6 Y values over here. Right? There's 6 Y values here. So I need to start with a 6 by 6 matrix to do this. You could type it in, but that seems silly. So for this, we want an identity matrix. The command in Excel for creating an identity matrix is munit. Another name for an identity from an algebraic standpoint is unit. So we'll call it unit, although we use units also used in just anything that has an inverse. So that's a kind of a semantic problem, which is not a huge surprise in math. But anyway, munit means identity matrix. Notice that it asks for a dimension here. We want a 6 by 6 identity, so we just put a 6 in there and it'll make a 6 by 6 identity matrix. Again, the number you're going to put in there is how many data points you have. Okay? There's a 6 by 6 identity matrix. The next thing we need to do is create a 6 by 6 matrix here that we can subtract from it. Okay, so the way we can do that, there's a make array command in Excel. It takes 3 things. This last thing, we're just going to do it because it works. I'll talk a little bit about it, but it takes 3 things. First, how many rows and how many columns. Those are your first 2 arguments that you want to put into this function. Again, what size do we want for this one to have? 6 by 6, so your first 2 arguments here will be 6 and 6. Then this requires some function of the rows and the columns to tell it how to fill in the different things. That's what the function part means. The function that we're going to use is called the lambda function. Notice it even says, creates a function value which can be called within formulas. All right. So this lambda function is also going to take three pieces into it. The first piece is going to be what we're going to say what the row entry needs to be. The second piece needs to be what the column entry needs to be. The third piece is then a function of the row and the column. All right. We're only going to do it because it works. I'm putting in 2 letters in there, so that's a function of row and column. So that's why I'm using R and C. But we want the exact same value every single time, right? What is the value that we want every single cell to have? 1 over 6 in this case, right? So we're literally just going to type in 1/6 there. Okay. The make array argument requires 3 pieces. I could not get this to work just by putting a 1/6 in there. It required a function. So this lambda function works. This lambda function just says, okay, if I put in an R, a row, and a column, then I could, if you had something where you had a function defined in terms of row and column, you could put like R plus C in there if you wanted the row R, column C entry to be the sum of the two. You can do it that way. But in this case, we just want a constant function, so we put the 1/6, or the 1 over how many data points we have. And there it is. I know, it's a little clunky, but it gets the values done. I mean, if you want to literally just type in the number 1/6 and then just copy it, you can do that too. Which, honestly, at some point, that might be easier. But at least now you know a new function. What do we want to do with these two matrices? Subtract them. So I'll just take the entries, the corresponding entries, and subtract. And then copy over and copy down. And I've got too many in there. Where it's just those two cells subtracted. So A22 minus the H22. And then I just copied it across them now. And we just need to do the difference of those two matrices. Yep. All right, so we've got to use this matrix in a couple of different ways. So remember again that your R squared value is your explained part over the total sum of squares part, right? So the top part is the B transpose X transpose NXB, right? And the other part is Y transpose NY. So we've got a few products to do, but once we get those, we should get numbers out of each of those, and we can divide them, okay? So this is the N matrix, whoops. This is the N matrix that we're going to use here and here, right? Okay. But some other pieces that we already have X transpose somewhere up higher. We've got X somewhere up higher. I've got B up somewhere higher. and I've got Y somewhere up higher. I need the transpose of those two things first, right? Before I start doing some computations. Here's your B matrix here, right? So right next to it, I'll just put in the B transpose. If I could hit the R every time I want to do transpose. I'll just put it next to it so that I can see it. Okay. So there's the transpose. Here's my Y. So doesn't matter. I'll just put it down here because I have room. Just got to keep track of where it is. I'll do the transpose of my Y's. I just put it there because I had room. If you don't have room, you'll put it somewhere else. Or in a different sheet. You can do that too. If you'd rather have it in a different sheet. I'm just trying to keep everything here accessible so they can see what's going on. So far, so good? Okay. All right. So, doesn't matter. Let's say we'll do our SSE part first. I'll label that. So for your SSE, if I do all these computations, I might as well just work from left to right. Do this product first, take that, multiply it with that, take that, multiply it with that, take that, multiply it with that, right? We do have to do 4 multiplications. If you're clever, you might be able to nest your functions. I don't want to do that because I'll probably mess it up as we go through. But you could do the product of that with the product of that with the product. And you just keep on going all the way through if you wanted to, but that seems kind of crazy. So the first thing we'll do is we'll multiply. I need to do B transpose, which is here, with the X transpose, which is, I got to scroll up. That was this one, right? That's our X transpose. Right? Oh, you're right. That's the X. Thank you. Here's the X transpose. That would have given me an error because it wouldn't have been able to multiply the two together anyway. Thank you. There's the X transpose. Okay, so B transpose was here. X transpose was here. Thank you. Before I hit enter and it said, no, I can't do it. All right, what do we do next? Multiply what we just got by which matrix? The n, right? Where's the n? Over here, isn't it? That was the thing we just computed here. What do we multiply that by? The x. I'll go grab the right one this time. So it's what we just computed times the x. The x is up higher here. So what we just computed times the x matrix we just had, which is that one. And then finally, what do we do with that? Multiply that matrix by the b we've got, which is here. At the very, very end, what should we end up with? Just a number, right? A 1 by 1, which is what we get. So there is our sum of squares, or sometimes it's called the error sum of squares, but it's the sum of it's the amount of your deviations of the predicted values from the mean of the data points. Okay. That's the sum of the squares of that. Okay. So this is your explained part, right? Yeah. Okay. I also need the total sum of squares, the SST part. To do that, y transpose was, I put that up here. That was right here, right? That was the transpose of the y's. What do we multiply that by? The n, which is here. And then finally, we take that matrix we just found and multiply it by what? The y's, which is up here. And get that. So finally, then, if we want the r squared, what do we do with those two numbers? Divide them, yeah. The very last thing we do is divide. Pretty good model. Remember, again, the closer you get to 1, the better the model is. This is pretty darn close to 1, which is not a huge surprise because I literally just took a random number between negative 0.1 and 0.1 and added it to the output of an x squared. So just moved it off a quadratic a little bit to get the data. So it should be really, really close. Yeah.
I'm sorry, how did you get SST?
Which part? This one? This one? Okay, so again, remember the first part is y transpose times the n. So your y transpose, we put wherever you put your y transpose, I put it up here, and multiply that by your n, which is over here. Oops, over here. Yep. Again, we could check this in R pretty quickly. Let me make a new file here and save it as a CSV real quick. Let's save this in. It's in my documents already. I'll call it data again. You can oops, not in Excel. Although you can do read Excel in R as well, but I always worry about the random different things that when you say something as an Excel file puts it in there as and having it not read the characters properly. If I do it as a comma separated values file, there's literally data and commas and end of lines. That's all you get. Okay. So strip off all the other stuff. All right, so if I can get back to my desktops and open R. All right, so I'm going to load that data I just made. All right, just to see that it really is in there. That was this file we just saved, right? Okay. So then again, remember, we can save our model as some variable name. I'll just call it model. Remember, the LM stands for linear model, but it means that you're linear in the coefficients, right? Not linear, the type of function you're trying to create. It means it's linear in the coefficients. The syntax for this, again, you reference your y values and you want them in terms of the x values, right? So since I pulled in my information and called it data, and I've got headers here, whatever the headers happen to be, I can reference those columns by doing the name of the data piece that I pulled in, and then the $sign and whatever the header is for that column. We talked about this last time, but just to remind. Okay. This is what would give us a linear piece, but we wanted that quadratic piece too. So remember, anytime that you want to say, hey, also add an extra term as a function of that variable, you put that function in there. So in this case, we also want to consider the square of the x values. We put that in the I of command, so that we have a function of the data that we want. And then again, same syntax here. I'm referencing the x values in the data that we have saved, and I want to square it. And then remember again, to see all the information in the model, we use the summary command, summary of the model. Gives you lots of information, but these values right here should match what we just came up with in the Excel file. Do they match? Yeah, they should match exactly what we got in the Excel file, by the way. It shouldn't be just be close. They should be exactly the same. Otherwise, we've made some error somewhere. The other thing that we should notice is the R squared. This is rounded to 4 decimal places, but rounded to 4 decimal places, is that what we got? Yeah, because we got 0.99988 or something like that, right? So all these things match. This one?
Yeah. More. I just want to see the model one. That's
okay. So this is just checking to make sure what we had in Excel was good to go. Was okay? We can also do the exact same thing if we want to create the output as a function of 2 variables. So let's do an example of that real quick while we're at it. Let's go back over to the regression data file here, and I'm going to click on that multiple tab. So the idea here is that we have 2 inputs and an output that we want to create. Okay. Whatever that happens to be. So say, for example, maybe you've got data that is air temperature and wind speed, and you want to know something about wind chill, for example. Okay. This is an idea of having 2 inputs and then getting an output. You can imagine lots of different scenarios. If you want more complicated things, maybe you're trying to predict grade point average of a student based on ACT score, high school GPA, all sorts of different things. Okay. You can think about a whole slew of variables trying to predict one thing. So that's the idea behind multiple regression, but it's the same idea. If we're doing a linear model, it's linear in the coefficients. So in this case, we would have, again, a constant, something times the first x, and something times the second x. Really, this is the same concept that we just did, except that our second variable was the first variable squared. It's literally the same concept. Okay? So we would do exactly the same thing. It's just a matter of what does our function look like when we're done. So we would create it the same way. So the coefficients on the x is all, the coefficient on the a all the time will be 1. On the b, it'll be x1 values. On the c, it'll be x2 values, right? So same idea here. Oh, this is all centered. It's all right. Make a column of 1s. Make a column of the x1 values. Make a column of the x2 values. So I just copied it over, right? This is your 1s for your coefficient on the a's, the x1s for the coefficient on the b's, the x2s for the coefficients of the c's. Again, to get your solution, the least square solution, what do we do with that matrix first? Transpose it. Good. Goes off the screen a little bit, but it's way over there, right? After we transpose it, multiply it. Take your transpose, which is this one that we just found, multiply it by the original. Again, what size, before I even hit enter here, what size should this matrix be? 3 by 3, because we have 3 parameters we're trying to find, right? A constant and 2 coefficients for each of the a coefficient for each of the variables. So again, before I even hit enter, I know what size matrix this should be in case something goes screwy. That's why I keep mentioning these things, right? If something goes screwy, you want to know where it might have gone screwy. After we find that matrix, what do we do next? Inverse of it, good. So do the inverse of that matrix we just found. One other thing I should mention with this as well. Notice that this matrix that you've created and its inverse both, they're symmetric, right? So look at my main diagonal here. My entries across that match up across the main diagonal are the same. You should end up with a symmetric matrix here as well. So you also know the size, and you also know kind of what the matrix should look like. Again, in case something goes crazy, right? You've done something incorrectly. All right. Notice also, this is also symmetric, right? See the symmetry? What do we do with this one then? Multiply it by the transpose, right? And then finally, to get our solution, what do? Multiply that matrix we just found, which is this one here, by the y's, which are way off over here. So this tells us that our model fitting this form would be negative 18.36827 plus 2.010185x1 plus 4.737812x2. That would be what our model would be. And again, if you wanted to predict, you can put in different numbers for x1 and x2 and get out y values. That's the whole point of this, right? If you're given some data and you want to try to predict some other things, you would put in the new values in your model and see what the prediction would be. And I'm sure you can imagine a whole bunch of scenarios where you might want to predict things. For example, from a university standpoint, one of the things that we would want to try to predict would be persistence of students, right? We want to know who might not make it to the next year. So we might have a bunch of inputs that we would put in and see if we have a predicted value to see who might be in danger of leaving based on our own data. And see what we could possibly do to help them. It's something that I want to do from a university standpoint. But there's all sorts of different scenarios that you can think of, right? The whole point of doing modeling and predicting and all those kinds of things. I mean, I'm guessing there's going to be a whole bunch of predictions, stuff popping up here in November trying to predict presidential elections and Senate elections and representative elections, all sorts of stuff along those lines. The website 538 will have all sorts of different ideas with different scenarios about what's going on with different simulations. Trying to predict that. Pretty much, if there's data for it, people are trying to predict something out of it. Okay. Why do you think they have shopping cards for grocery stores? Trying to predict what your spending patterns are and know what deals to send you to get you to spend more money. For example, everything's about collecting data and trying to make predictions off of it. Why do you think your computer stores cookies on your websites? Anyway, this is how we find the least squares solution. Next thing we want to do is try to figure out what the R squared value is, right? So again, we need to create that N matrix and do those products that we just talked about. How many data points do we have on this one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I need to create a 10 by 10 identity. To clean, I'll just do it on the same screen. So 10 by 10 identity, remember again, the command to create the identity matrix is that munit command. And then I just type what size I want. Identity matrix has to be square, which is why we only have to put in 10. We don't have to put 10 and 10. Okay. So there's our 10 by 10 identity matrix. We also need to create a 10 by 10 matrix with what is every single entry. 1/10, right? Again, you could just type it in directly and put in equals 1/10 and copy paste. Or if you want to do that make array command again, either way works. I want 10 rows and 10 columns. This just does it all at once, right? So the make array command again will do an array that has that many rows and that many columns. And then this syntax here will take in each row and column, it'll just put 1/10. Then I only have to type one command. I mean, you can do it the other way, right? I can put equals 1 divided by 10, or type in 0.1 and copy it into a 10 by 10 grid. Either one works. Okay. Again, the main point of me doing this, besides telling you about the theory about why this works and what you're trying to measure, is to teach you a little bit about how to use Excel in different ways, right? In practice, you're never going to do this, period. Okay? It's not the point of this. Okay? Just be thankful I'm not making you do it by hand. I'm teasing. I wouldn't make you do it by hand. That would be a complete waste of time. All right. What do I want to do with those two matrices? Subtract them. So I'll take each of them and subtract like we did before. So just subtract the corresponding entries, and this one I will just copy. Bless you. Copy across, copy down. Good news is I'll know when I'm out of places to... When I hit that row of zeros there, I know that I've copied down too far. I can just delete it out rather than having actually to count. That row, when I leave that blank in there, that row of zeros tells me how far down to copy, and I just cut it out. Yes?
Sheer curiosity, is it possible you can make a rate command to just do both those types of things?
Yeah, you can. Yep. Yeah. Or you can probably write a Visual Basic macro and do the same thing too. Yeah, you can absolutely do that. That was beyond what I wanted to do. All right. So now from this, we can calculate our SSE and our SST. So like before, let's do our SSE first. First thing I need to do, I'll get the transposes that I need. Remember, for SSE, I need my B transpose. Here was my B matrix. So let's just get that so I can refer back to it. Right? And for the SST, I'll need my Y transpose. For simplicity, I'm just going to copy these down so I can refer to them later. All right, so first thing we need to do is I need to take that B transpose, which we just found. That was this one here, right? I need to take that. I'm just going left to right. I'm going to do that multiplication, get an answer, then that multiplication, then that one, then that one. Just work from left to right. Okay. I need to multiply that by X transpose. X transpose is somewhere up at the top of the page here, right? Up here. So back down there, there's my command. I should see a single row at that point. After I do that multiplication, I need to multiply this matrix we just found by the N matrix, which is over here. That's this one here, right? That's the N. Again, you should see single row across. Just like we did before, right? Everything was a single row across. This one will multiply by which one? The X, which is up somewhere up here. Working our way across, right? Again, should see a single row, even a smaller row in that case. And then we multiply this row by which one? The B. So this one by this one. And get that. I know, a little tedious, but we get there. The SST is shorter, isn't it? Okay. All right. So for SST here, what are you doing? Why are you being weird? Okay. All right. For SST, I need to do the Y transpose times the N. I don't have the Y transpose yet, so let me put that down here so I can get it. Again, if you're clever, you can do nested functions and do it all at once. I'm just doing it in steps because I don't feel like being clever. Okay. Here I need to do the product of the transpose we just found, which is here, the Y transpose, with which matrix again? The N, which is over here. Again, should have a single row. What do we do with that? Multiply by the Y's. So that single row times the single column. I copied the Y's down so I didn't have to scroll everywhere, right? Get that. And then finally, to get your R squared, what do we do? Divide that. Oops, I actually need an equal sign. Divide that by that. Product, the quotient of those two things. Get 0.9255. That's a pretty good model, right? You have that R squared value around there. That's pretty good. In real life, you're probably not going to find an R squared that high. Life is more chaotic than that. That okay? Again, using R, we can check these things. So let me go make a CSV file out of this real quick. Oh, that's right. I already have it open. Let me get data 2 because I already have that open. Yes. All right. So same idea here. Let's read in that CSV file. Again, if I want to just type it in the data and see that I really did import what I wanted. Notice again, it's got the headers in here, x sub 1, x sub 2, and y, right? So again, just like before, if I want to make a linear model, I want to predict the y values coming from the data we imported, right? So I'll use that data, whatever name, I just gave it a name, data. You can call it whatever you want, okay? Whatever you want to call it. The important part is that you, whatever name you gave it, you use the $y to talk about that variable you're trying to predict, and then the independent variables go second, okay? So we want to do this in terms of the x's that we have and the y's that we have. Since both of them are just literally constant times the variable, I don't need to use that I of command, right? So the syntax is that. And then finally, again, if we use the summary command, we should see all the pieces of information that we got before. Here are your coefficients that we just found. Do those match? And does your R squared match? Yeah, and it should. Okay. These values on the end are for statistical purposes. And if you wanted to know more about how to use those and how to take different things away from those, you take a statistics class. That's something I'm interested in. Just trying to get the models here and a little bit of an interpretation idea. Questions on that? That's literally what I would expect you to do on Excel. And then again, you can check your answers in R pretty quickly. Actually, you can check your answers in any program that has statistical packages built into it. So for example, given a set of data, you can run linear regression in Excel and it'll spit out the same numbers and check it in Excel. Any questions? Yes.
On the homework, like it says to predict the temperature that would produce an efficiency of 50%. How would you go about it?
So, so you've got the temperature in terms of you've got efficiency in terms of temperature.
Yeah.
So if you want to set, you would set your efficiency equal to 50% and solve for t. Yeah, whatever function you come up with is solve. Yeah.
I take it that is not due today because I definitely thought it was.
Oh no, it's not due today. Yeah.
Okay.
Yeah.
My bad.
No, it's okay. It was originally due today, but we didn't get this done last time, so that was why I went ahead and pushed it back to Tuesday. So if you want to take it back and work on it.
Yeah, I will take it back.
Mm-hmm.
Speaking of which, for R squared, that equation, obviously I did not know about that until just now.
Yeah.
But does the sum of squares of both still work? Does it in essence calculate that, or do I have to read that part, which is fine?
This calculates the sum of squares.
Okay.
Yeah.
So if I just actually summed up all the squares of both, it would work.
Usually have the exact same numbers. Yes.
Okay.
Yeah. Is that right?
It wasn't that bad. I'll still use Excel.
Yeah, you can do it in Excel. Absolutely. Good. Is that right? So let's go on and extend this idea of least squares stuff to things that aren't necessarily data points and data values, but to functions. So today we are going to talk about Fourier series, start Fourier series stuff. All right, so what you were doing with the least squares ideas was trying to minimize that difference between predicted value and observed value, right? That's the idea. And we did that. Basically, what we're doing that was with idea of distance, correct? When we did that E transpose E idea, when we were doing that with values, that was our sum of squares of differences between those two things, correct? But if you think about this as distance in Euclidean sense, or if you think about it in terms of size of vectors, magnitude of vectors, norms of vectors, this really is the magnitude of your y minus xb squared, right? That's the idea. We really are looking at the difference between these two things, and what's the distance between these two things as vectors. And again, we want that to be as small as possible. That was the idea behind the least squares, correct? Okay. So the idea was we want to make, if I think of the b now as a variable, we want to make this quantity as small as possible. That's the whole idea of the least squares idea, is I'm trying to make this distance notion as small as I possibly can. Probably not going to be 0, because if you get, we already know that if you get more equations than you have variables, a lot of times you get contradictory information and you can't find a unique solution. You can't find any solution, right? So instead, we're trying to minimize this distance as much as we possibly can. Okay? Again, thinking about the b as the variable and solving for what that b has to be. Okay? Well, we're doing that. What we just did was in a Euclidean sense, right? We had data points that we could subtract and look at, kind of look like a dot product idea, right? Notice that this would be, if I think about this as our y1, y2, out to yn, and you have a y hat 1, a y hat 2, a y hat n, right? The difference, this magnitude, that's right. This magnitude here is your, let me call this y and y hat. This is your distance between y and y hat computation squared, right? From a dot product perspective, okay? You would do the dot product of this with itself. That's what we get, right? Okay. So what we're trying to do here is really minimize a dot product idea. Well, good news is that dot products extend to other types of spaces besides just Euclidean spaces. In particular, we're going to look at a dot product in function spaces. So we write this notation this way. This C stands for continuous functions. And this is just on the interval AB. So I'm going to use this notation. I just want to make sure that we're all on the same page of what I mean by that notation. All right. So in the set of all continuous functions from on the interval from A to B, we can define a dot product. We call it an inner product. The notation for inner product looks like this. Rather than using a dot, we use pointing brackets around the two functions. This is why we want to make sure the functions are continuous. We want to make sure our definite integral exists. So we can define an inner product by doing the product of the two functions and then integrating it from A to B. What inner products allow us to do is give us an idea of distance, how far apart things are. Okay? So if we want to try to find a least squares solution for a function, what the idea is we want to try to find a function or a set of functions that give us this thing being as small as possible, again, the distance, right? So if I wanted the distance in the terms of this inner product, if I wanted the distance between these two functions, and I'll do it squared again, just so I don't have to worry about the square root. If I want the distance between those two functions, I would do the inner product of the difference of those two functions squared. That's how I would find the distance between those two functions. Notice it's the same idea, right? I'm doing the inner product of the function, the difference of the functions with itself, right? But it's not Euclidean anymore, it's functions, okay? So the idea behind what we're going to be doing with Fourier series, or trying to do this in general with approximating functions, if I'm given an f, I want to try to find a g so that among all the possible functions, this distance is minimized. It's still at least squares idea. Okay, that's our whole point. I want to try to find something that minimizes this. Good news is that we don't. Well, we have to do integrals eventually, but to get this to work, we don't have to actually understand what the integral has to be. Okay. All right. So, what's the idea behind what we're going to do and then how it works? Okay. So, let's say, and I think I've tried to draw this picture before, but let's say you've got a whole space of solutions. Again, let's think about the x as the matrix and the b as the variable again. If I think of my x being a bunch of vectors and being doing this product, then this has a whole bunch of vectors that live in this space, right? And if I'm in this space, I'm happy. I can get combinations that give me the vectors that I need. But what I'm interested in is, let's say I had some other y that's out here that I want to try to approximate. Let's say my y is not in the space. Okay, so I've got a whole bunch of vectors down here. I want to use these vectors to approximate this other vector that's not in there, this y. So this y is sticking up off this plane the way I have it drawn. Okay? If I want to try to find something in my plane, I have it drawn as a plane here. If I want to find something in my plane that approximates this thing as best as possible, what do you think I might want to do with this vector? From a kind of a geometric or a picture standpoint, what do you think I might want to try to do with this vector? If I want to find the one that's the best one down here to approximate it, what might we want to do? Yeah, just smush it down perpendicularly, right? Do what we refer to as a projection. Smush this down, take a shadow, right? And use that for my prediction. That's the best, right? Because this distance right here will be the smallest if I use that projection, right? So anytime, from a geometric standpoint, if you're trying to find a least squares solution, you're really looking at this projection idea here, trying to figure out what this projection is. Now, all that work that we did with the Euclidean vector stuff, or the data that we just used before, is finding that projection. We're finding what that projection is onto, well, a lot of cases it was a plane, but onto a set of vectors that we have generating some space. Okay. We want to do this from a function standpoint now rather than a set of data. So we have to talk about how we find this projection onto a space. Well, if you remember back in, maybe in calculus class, if you've had some vector calculus stuff, if I just look at, maybe I have a V1 here, and say I have V2 here. When you do projection down this way, we can calculate this vector here. This would be your projection of V2 onto V1. That would be the vector that we're looking for, right? The way we can do this, and I'm not going to go through all the work because some of you have seen the work, and if you haven't seen the work, you'll see it eventually either in Calc 3 or linear algebra. One of the two, or both. Okay. You do the dot product of the two vectors over the dot product of the vector you're projecting onto with itself times the vector that you're projecting onto. In particular, notice what this format looks like. I take the dot product of the vector that I'm projecting onto, sorry, the one that I'm trying to project onto the one I'm projecting to, right, on the top. And then we also divide out then by the square of the length of the vector that we're projecting onto. Okay. All right. So that's our idea. So generally speaking, when we do this, we need to do this for a whole set of functions. It's a lot easier to do this if we have a set of functions that have certain properties. And given the fact that I've got about a minute, I think I'll stop there. But it's a lot easier to do this if I have functions that are mutually, we refer to it as orthogonal. From a geometric standpoint, orthogonal is basically perpendicular. And we can compute these projections really easily if we have perpendicular things to start with. Okay? So we'll talk about that a little bit next time. And then talk about how we get Fourier series, and then we'll play with GeoGebra a little bit to help us get these things. So, all right. Have a good one. Your homework for the least squared stuff will be due on Tuesday. Have a good one.